All right, let's take a look at our fifth example from Chapter 6. Air is compressed in a steady state insulated flow device. So, steady state insulated, take to be adiabatic flow device. The air enters at 1 bar 25 degrees C and exits at 5 bar 200 degrees C. Determine the amount of work needed for this compression. Calculate the entropy generation. And then what is the minimum amount of work necessary to compress the air from 1 bar 25 degrees C to 5 bar, and what would the temperature at the exit be for part C. We're told we can assume air to be an ideal gas with a CP of 30 joules per mole Kelvin. Alright, so let's start with, I'm going to call it, part A and B. We'll just kind of solve both of them together. So I'm going to start with my picture. Okay, so here's my compressor. Air is going to enter at a temperature of 25 degrees C and a pressure of 1 bar. Then air is exiting at a pressure of 5 bar and a temperature of 200 degrees C. Okay, it's insulated, so I'm going to take insulated to mean that there's no heat exchange between my system and surroundings. Okay, but there's going to be some necessary work. All right, so here it'll be shaft work in order to compress my to press air from these conditions to these conditions. All right, so let's start. So AS, let's calculate the work. So just looking, I know my inlet temperature and pressure. I know my exit temperature and pressure. So the state of my system is completely specified in both cases. So let's start with our first law of balance and calculate W. All right, so I'm going to start by writing my general first law of balance for my open system. So that'll take the form of du total dt plus delta. I'll have change in kinetic energy plus potential energy plus enthalpy. Remember, enthalpy, not internal energy, since my fluid, my flowing fluid element needs to displace the fluid element in front of it. Okay, so that's an m dot, and that'll be equal to Q plus W. All right, so in the problem, we're told that our process is adiabatic, so Q is equal to 0. So that is good. So let me just adiabatic, which means that Q dot is equal to 0. Okay, we're told in the problem statement that we're operating at steady state conditions. So that tells me that my accumulation term is 0. I also know then that my inlet and outlet mass flow rate, right, need to be the same. So steady state, and then I'm going to assume that our change in kinetic energy and potential energy is negligible. Okay, so therefore my kinetic energy term and potential energy term are negligible or 0. So my first law of balance for this problem reduces to H2 minus H1 times m dot is equal to W dot. Now if I divide through by m dot, okay, W dot over m dot, this is work, so my rate, so energy per time. Okay, this is mass per time. So this just works out to mass, or W, my specific or molar work. So my first law of balance for this problem is going to be H2 minus H1 is equal to W. All right, so for my ideal gas, okay, I have that W is equal to H2 minus H1, which will be equal to the integral from my initial, or my inlet to my exiting state, or initial to final, of Cp dt, where we're given a value of heat capacity, which is independent of temperature. So this is going to be Cp ideal gas, T2 minus T1. All right, so calculating. Okay, so if I jump over to MATLAB, bam. Okay, let's start with my heat capacity. Heat capacity is 30, and that's joules per mole Kelvin. Keep it in SI units. T1 is 25, and I'm going to convert to Kelvin. Okay, because I'm assuming when I have to calculate my entropy generation, I'll need a ratio of temperatures. And so it's important that I have absolute units. T2 is 200. So I'll add 273.15 to that to convert to Kelvin. And so then W is Cp times T2 minus T1. And this work, okay, is going to be in units of joules per mole. Okay, so running, I get 5,250. Okay, and so it's positive because work needs to be done on my system. So W is 5,250 kilojoules per kilogram. It's positive because work needs to be done on my system. All right, so if I think of an air compressor, I've got to plug it in. All right, work needs to be added to my system. All right, so there's W. And then B, calculate the entropy generation. Well, to calculate my entropy generation, thinking back to chapter 4, right, S gen is going to be equal to delta S of my system plus delta S of my surrounding. Okay, where I'm going to take delta S, and actually let me just write it out separately. I'm going to take delta S of my surroundings. I'm going to take my surroundings to be a bath. So that's Q bath over T bath. Okay, where Q bath is going to be negative Q, right? Any heat, say, released by my system would be absorbed by my bath. But since, right, we're told this is well insulated, all right, it's insulated, so it's adiabatic, so Q is equal to 0. Okay, there's no heat exchange between my system and surroundings. So I'm just left with S gen is equal to delta S of my system, which is going to be equal to S2 minus S1. All right, so I need to calculate S2 minus S1. Now this is a case in which neither temperature nor pressure are being held constant. Right, so we've looked at plenty of these cases for an adiabatic process. The text even gives an expression for the general change in entropy from some initial condition to some final condition. I always seem to work it out because just because, right? So I'm going to do that here for the case of an ideal gas. Okay, so if I want to get S2 minus S1, I go back to my definition of entropy, and I'm going to write it as TdS is equal to dq reversible. Right? Usually ds is dq reversible over t, and then I multiply, but we'll keep it at this for now. All right, so TdS is equal to dq reversible. To get dq reversible, I think to my first law. My first law is, in differential form is du is equal to dq. Okay, I'm going to write as reversible up here, right? Because I'm dealing with a reversible process. And then I'm assuming the only work term, or all I write is dw. But then I'm going to assume the only work is via boundary work. So that's going to be a minus p dv. So solving for dq reversible is going to be equal to du plus, got too many dv's here, p dv, plus P dV, where du is equal to Cv dt. And that's plus P dV. All right. So now this is equal to T ds. So ds then is equal to Cv over T dt plus P over T dV. Now remember, for an ideal gas, Cp is equal to Cv plus R. All right, now remember, we're dealing with an ideal gas, right? So this is where now we put on our ideal gas hat, if you will. Okay. So we're given a value of Cp and it's constant. So Cv must therefore be constant as well. So if I integrate from my inlet to my exit, or initial to final state, okay, what do we do, right? And okay, I've got to take one step before I do that. Okay, well, let me get the first two. I'll just write this S2 minus S1 is equal to, so if Cv is constant, I pull it out, and then integral from 1 to 2 of 1 over T dt is log T2 over T1. All right, now before I could tackle this last term, okay, I have P here, I have T here, both which are changing for my process, and I need to integrate that with respect to V. Well, key is, for an ideal gas, PV is equal to RT, so you find that P over T is equal to R over V, where R is a constant. All right, so this could be integral from 1 to 2, R over V dV. So S2 minus S1 is equal to Cv log T2 over T1. R is constant, so plus R. Integral of 1 over V dV is log V2 over V1. Okay, so that's fine. I can use V, okay, but I can simplify by using my ideal gas equation of state. So I know that P2 V2 is equal to R T2. Okay, P1 V1 is equal to R T1. Boom, boom. Okay, cancel my R's. Therefore, I get V2 over V1 is equal to T2 over T1 times P1 over P2. Okay, I could plug that in here. S2 minus S1 is equal to Cv log T2 over T1 plus R log T2 over T1 times P1 over P2. Log rules, okay, Cv log T2 over T1 plus R log T2 over T1 plus R log P1 over P2, right? Multiplication is equivalent to addition of logs. Okay, now collecting like terms, okay, I get Cv plus R log T2 over T1 plus R log P1 over P2. Okay, where Cv plus R is just equal to Cp. Okay, so I get my general expression for my change in entropy. S2 minus S1 is Cp log T2 over T1 plus R log P1 over P2. Okay, so that gives me delta S, which in this case is equal to S gen. All right, so good. I've got my temperatures already in absolute units. So let's get our pressures in MATLAB, R, and we can calculate S gen. Okay. So R is 8.314. That's joules per mole Kelvin. Get my pressures. P1 in bars is 1. P2 in bar is 5. Okay, so therefore Sgen, which is equal to, and actually let me calculate, I'll call it DS system, and Sgens could be equal to DS system. That's going to be equal to CP times natural log in MATLAB is log T2 divided by T1, where again we had converted to absolute units for temperature, plus R times log again is really natural log P1 over P2. I call it P1 bar divided by P2 bar. So bar here is fine, right, as long as the units of pressure are consistent and they're absolute, not gauge pressures. Whew. So I get DS system is 0.4736. So I get S2 minus S1 is equal to 0.4736. And that's going to be kilojoules per kilogram. No, I'm thinking in terms of steam tables. That's going to be the same units as CP, which is in joules per mole Kelvin. Okay, it's going to be the same units as CP, which are the same as R. All right, CP is joules per mole Kelvin. Okay, and so then Sgen is going to be equal to S2 minus S1, so it'll be equal to 0.4736 joules per mole Kelvin. So Sgen is positive. That's good. All right, that tells us that our process is irreversible. All right. So now we have we've calculated work for A. We calculated entropy generation B. Okay, now C. So now C and D I'm going to tackle separately. Okay, because we'll see in a second. So that was A and B. So C and D I'm going to tackle separately. Because what's going to be different, okay, is now I'm going to have my same inlet stream. So I'm still going to have air at 25 degrees C and 1 bar. Okay, but now my exit is going to correspond to, we're just told it's at 5 bar, and we're told that we want the minimum work. So this is going to correspond to our process where Sgen is equal to 0. All right, so they want the minimum work to compress our gas to P2 is equal to 5 bar. Right, that's our same pressure as before. Okay, but now T2 is not known. T2 is not known. Okay, in the problem statement, okay, they tell us that we're insulated. Okay, so I'm still going to assume. That this is adiabatic. Okay, I'm still going to assume that Q is 0 since we're well insulated. Okay, I need to calculate the work again, but what I'm also given this time is we want the minimum amount of work. The minimum amount of work is going to correspond to the case when my entropy generation is 0. All right, the minimum amount of work is going to occur for a reversible process. Okay, so let's do it. Okay, so let's solve for the case when Sgen is equal to 0, and let's get T. So we're gonna have Sgen is equal to 0, and with Sgen equals 0, we want to solve for T2 and W. Can we do it? Sure. Of course we can. All right. So I'm going to start with my entropy balance. Okay, so if I go to my entropy balance again, okay, I'm going to actually, borrow a lot from what we did just here. Okay, we had that the entropy of our surroundings is 0 because our system's well insulated, so there's no heat exchange between my system and surroundings. So Sgen was equal to S2 minus S1. Okay, so we had Sgen was equal to S2 minus S1, which, for an ideal gas, was equal to Cp log T2 over T1 plus R log P1 over P2. Okay, and now we're told that our entropy generation is, or for the reversal process, our entropy generation is 0. So looking, I know P1 and P2. I know T1, I don't know T2. All right, so using this one equation, we have one unknown, T2. Let's start by solving for T2. All right, let's give it a try. So then we have Cp log T2 over T1 will be equal to negative R log P1 over P2. We have a negative sign, so I can flip flip my ratio here. So log rules. That's R log P2 over P1. Right. Essentially, I could bring my this term in front up as an exponent. Right. So raising something to the negative 1 is the same as inverting it. Okay. So let me divide by R to make this dimensionless, and I'm going to get Cp over R log T2, and actually I take that back. I'm going to divide through by Cp because I'm going to eventually want to solve for T2. So let me write this as log T2 over T1 is equal to R over Cp log P2 over P1. And so that'll be equal to log, I'm going to bring R over Cp up. Okay, and so, yeah, I'm going to try and get this right. P2 over P1, bring that up, R over Cp. Okay, actually, I don't know why I need to write all these parentheses. Okay, so the natural log of P2 over P1 raised to the R over Cp. All right, so now let's take the exponential of both sides. And that would give me T2 over T1 is equal to P2 over P1 raised to the R over Cp. So T2 is equal to T1 P2 over P1 raised to the R over Cp. Phew. Okay, where for temperature, I need to make sure I'm using absolute units. So let's go over to MATLAB and let's solve for T2. Okay, so this will be for the case when Sgen is equal to 0. Okay, so I get T2 is equal to, okay, so T1. Okay, so I'm gonna clear T2 because we just T2 from the previous calculation, even though I'm overwriting it, so it shouldn't matter. But T2 is going to be T1. Now T1, we've converted already to Kelvin, right? So we're using absolute units. So then we have P2 divided by P1 raised to the R divided by Cp. Okay, and let me just make sure Cp is 30. All right, Cp is 30. Okay, so that'll give me my temperature in Kelvin. If I want to get it in degrees C, just for illustration, that would be T2, which I just calculate, minus 273.15. Okay, so P2, and it's because I call these bars. Let's try again. All right, so I get T2 in degree C is 192.5891. So T2 is 192.5891. That's degree C. And that would be equal to 465.7391 Kelvin. Okay, so for this reversible case, right, my exit temperature is cooler than for the irreversible case. So that's cool. And, it makes sense because we expect less work to be needed. So there's the exit temperature that they ask for. But they also ask for the necessary work for that reversible case when Sgen is equal to 0. And to get that, okay, I'm going to go back to what we'd worked out for A and B. My first law of balance for this problem is just H2 minus H1 is W. So W is Cp ideal gas, T2 minus T1. Okay. So I get that W is equal to Cp ideal gas, T2 minus T1. Whether I use Kelvin or C, since I'm taking a difference, doesn't matter as long as I'm consistent. Okay, but solving, we get the W. So I get the W is equal to Cp times T2 minus T1. And that's 5,027. 0.7, is that right? And that is joules per mole Kelvin. So the minimum amount of work necessary occurs for the reversible case. We get 5,027.7 joules per mole Kelvin. For the irreversible case, right, it's larger, it's 5,250 kilojoules. And I'm thinking in terms of steam tables, this isn't kilojoules per kilogram. This is joules per mole Kelvin. Okay. So my apologies. After all those problems for water, I was thinking in terms of steam tables. Okay. Here, for our ideal gas, that's joules per mole Kelvin. All right. My entropy generation is joules per mole Kelvin. Okay. So, work is not joules per mole Kelvin, it's just joules per mole. Okay. Joules per mole. So work is 5,250 joules per mole. All right, Sgen, all right, entropy has units of joules per mole Kelvin. And then for the reversible case, the work is smaller, about 500 joules per mole. So we go from 5,250, so about 200 joules per mole smaller. So this isn't joules per mole Kelvin. This is just joules per mole. All right. And that's all they ask for, right? Because they want the exit temperature and the work. Yeah. So hope that helps. If you have any questions, let me know.